There we go. All right, so I'm gonna start right now. And all right, so more or less I'm gonna go through what we did yesterday and add a little bit of new content because I think I rushed a bit through yesterday's workshop, and I think it'd be good to go over a bit of what I said. So changed a bit the notes to get a sort of better picture with better examples of what's going on. All right, so overall, our goal is whenever we study regression so far is we try to look at one dependent variable and see how can it be explained by another variable. And the way we would do this so far is by looking at observed points. So we have data on our independent variable and our outcome, y, and we see how the variables fit together. And the way we want to measure that relationship is by crossing, try to find the best fitting line between the points. And when we are measuring our, when we were trying to measure one variable as a function of just one other variable, one explanatory variable, that was a single linear regression model that you guys saw in class. And now we are trying to extend that with the multiple regression model. So I wrote as an example, I'm trying to simplify things and just focus on a multiple regression variable with 3 parameters, beta 1, beta 2, beta 3, and having our outcome, which I just, sorry about that, which I measured as sales to be a function of advertising and prices. So the economic model that we have here is that sales is a function of advertising and price, a linear function of that. So it'd be beta 1 plus beta 2 advertising plus beta 3 price. So on one hand, beta 2 measures, it measures the relationship between advertising and sales. So as you've seen in the simple linear regression model, if you take the derivative of sales with that respect to advertising, you get beta 2, which means that a unit increase in advertising leads to a beta 2 increase in sales. And the same thing can be done for beta 3 with regards to the price. So that was our economic model. We suppose that sales is a function of advertising and price. Now we want to see how do we translated it in terms of a econometric way. And the way we do this is saying that sales is equal to beta 1 plus beta 2 price plus beta 3 advertising plus this constant, the error term. And the error term captures, well, it essentially captures all the different factors that affect sales that are not represented by price or advertising. So one example I can give you such as, let's say total factor productivity, things such as like the good weather, or just for that matter, the COVID crisis. You'd expect sales of companies to go down because of the COVID restrictions and what's been going on today. But this is not captured obviously by the price nor advertising. So everything that affected sales from COVID, for example, is captured in the error term. So that's our econometric model. Beta 1 plus beta 2 price plus beta 3 advertising plus the error term, which is everything else that measures the effect on sales. Regarding that error term, so I said last week that we assumed it followed the normal distribution with mean 0, meaning that over time the error term just cancels out, and it has a variance sigma squared, which is constant. So across all different observations we have of our independent variables, price, advertising, and sales, over all of these observations, the error term each time is going to have a constant variance. Last thing I want to point out is how do we visualize the error term, more or less? Well, as we had before, we have our set of points, and we try to draw, we estimate the relationship between the variable y and the variable x through our regression line, and the error term obviously is going to be measured by the difference between our estimates and the observed value. So this is the observed value, and this is our estimated value. The difference right here is obviously the error term. And we can do this across all observations. So here, right here, right here, right here. All these are the error terms. And yeah, just one thing that I want to point out is these error terms right here, they're the observed error terms. And since they're observed, I'll just put a hat over it, all right? Theoretically, this is a residual, so it's not really observed. But when we look at our model estimation and what we have in terms of values, taking the difference will give us the estimate for the error term. So that's about it. We have EI hat, which is the estimate for the error term, which is the difference between the observed value yi minus the estimate that we predicted for yi, which is just yi hat. So whenever I put a hat, it just means that well, it's just an estimate for the random variable. All right. So, well, since sales is equal to, in the econometric model, since sales is equal to this, well, the expected value of sales is going to be the expected value of this. Since all of this right here is a constant, then the expected value of sales is just going to be this constant right here, because the expected value of the error term is 0. And on the other hand, the variance of sales, or the variance of our dependent variable, is going to be the variance of all this, which is a variance of a constant plus the variance of this, and that is just sigma squared, as I said, as I just said here. So going over quickly our model assumptions, we have, all right, our dependent variable, which is random, which is a function of beta 1. Sorry, I wrote that wrong. Let me just correct this. We have beta 1 plus beta 2 x2i plus up to beta k xki plus the error term. And later on, we will estimate it through yi hat, because beta, as I said, beta 1, beta 2, beta k, these are all population parameters, which we don't know. So we're going to estimate those parameters. So we have an estimate for yi, which is yi hat, which is equal to b1 plus b2 x2i plus so forth bk xki. All right. So yi hat is our predicted value for yi, and it's based on the predicted values for beta 1, beta 2, beta k, which is b1, b2 up to bk. The expected value of yi is, well, it's equal to this term, simply because the expected value of this is equal to 0, and all of this is a constant. The variance is equal to sigma squared, as I said before. We said before that the covariance between the error terms across different observations is equal to 0, which in turns implies that the covariance between the dependent variables is 0 across all different observations. And the last thing that we said, which was quite intuitive, is that the independent variables, which is well, in our example, advertising, price, all of these are observed and they're not random. So we have sort of data points and values regarding these variables. All right. So then we talked about the estimation procedure for the, so essentially we had our econometric model and we want to estimate our model through yi hat, which is equal to, well, I'll just go back to the example to make things clear. You want to estimate sales. So sales hat, which is equal to B1 plus B2 advertising plus B3 price. Plus B3 price. So that's our estimate for sales. And what we need is to get those beta 1, beta 2, and beta 3, which is the estimates for the beta 1s, beta 2s, and the beta 3. And the way we would do this is, again, try to minimize the errors that we have between, well, what we would predict and what the actual outcome yi is. And that is captured through this yi minus yi hat squared. And that in turn is equal to yi minus, and this term right here, yi hat, I can just replace it with, well, beta B1 plus B2 advertising plus B3 price. That's just what I did right here. And as I said before, I'm minimizing the squared of the error terms. And the reason why is because if I have a positive error term and a negative error term, when I sum them up, well, they might just cancel out, and it will show as if there is no error, when in fact there is. It's just one was negative, one was positive. They just canceled out, and it made it seem as there was no error. So we square everything to make sure that we don't run into that confusion. So we want to minimize this function right here. We want to minimize this by getting essentially the values for B1, B2, and B3 that minimize this whole expression, this whole summation. And the way we would do this is by taking the partial derivatives of this expression, which is just the partial derivative of this expression, with respect to B1, B2, and B3 each time, giving us a system of 3 equations with 3 unknowns, and we just need to solve for B1, B2, and B3. So yeah, that was about it. Then I talked about the estimation of the error variance, sigma squared. So again, in our model, we had that yi was equal to beta 1 plus beta 2 x2i plus beta 3 x3i plus the error term. Well, we know this is a constant, and the variance of this is equal to sigma squared. So the variance of a constant plus sigma squared, the variance of a constant plus EI is just going to be sigma squared. So again, the variance of yi is just equal to sigma squared. And the way we would estimated it is to take the unbiased average of the sum of squared errors. What I mean by that is we take the sum of the observed errors, EI hat squared, which is the sum of the difference between the observed values of yi and the estimated values of yi, square them, sum them up, and divide by n minus k, where n is the number of observations we have, and k, on the other hand, is equal to the number of parameters we have in our model. So in our example, when we had sales is equal to beta 1 plus beta 2 advertising plus beta 3 price, well, we had 3 parameters, so k would be 3. In the simple regression model, k would be 2. So that's how you would estimate sigma squared, and we will just write it as sigma hat squared. Following that, we have we want to look at the sampling properties of the least squared errors, and notably, we want to see the distributions of. You want to know the distributions of B1, B2, up to BK, because these are random variables depending on our sampling and our observations. Whenever we try to estimate B1 up to BK, we might get different values. So we want to know what are the distributions of that. I talked quickly about the Gauss-Markov Theorem, which just relates our estimation procedure right here, which is the least squares method. It just says that the yielding result, B1, B2, B3, gives us the unbiased estimators with the smallest variance. There's an interesting proof for that, but it's in one of the, it's not in the textbook that you guys are using. I think it's another econometric textbook, but if you can look it up on the internet, I find it quite cool. So you guys should check it out. Other than that, yes, one really important thing to notice, and you guys probably did that in class, with Saraswata, is that you were able to write B1, B2 as a function of the independent, as a linear function of the dependent variable. What I mean by that is you guys were able to write BK, I think it was summation of yi, wi, yi, where this is some weird expression, but essentially, again, the BKs are just a function of the dependent variables. But since the dependent variables follow a normal distribution, then it must be that a linear combination of normally distributed random variables will also follow a normal distribution. So we have that for all k, we have that the BKs follow a normal distribution with mean beta k, and let me just correct this, and variance, well, variance of BK. And I talked about the variance of, so if we had our model, our estimated model, yi, which is equal to beta 1 plus beta 2x2i plus beta 3x3i, the variance of beta 2 right here is equal to some really complicated long expression, which is denoted right here. It's the variance squared. Since we don't have the variance, we just estimate it using the formula we had. So that would actually give us an estimate for the variance of B2, measured by the hat right here. And all of that is divided by 1 minus the sample correlation between x2i and x3i times the summation of x2i minus x2 bar squared. And the sample correlation is given by this really weird formula between x2i and x3i. One important thing to notice is if this value right here is 1, then the whole denominator is equal to 0 and the model just completely fails. So something I talked about it yesterday, it's really, really important that your independent variables, in our example when we had, I think, advertising and price, that these two variables must be as uncorrelated as possible. And what that means is if we increase price, but price is perfectly correlated or uncorrelated with, negatively correlated with the advertising, then the effect on sales can't be measured by beta 3, but more as a function of beta 2 and beta 3. And that just creates a whole failure in our model. And that's just not possible. And again, the higher the correlation between your independent variables, the least precise your model is going to be, by having a really high variance for B2 and the estimates of your econometric model. So again, I wrote a few notes about this formula. So the larger the larger the estimated variance in our model, the larger the variance in the estimates for the beta 1, beta 2 up to the beta case. It makes our model overall less predictable and more volatile, as written right here. So the less randomness we have in our observed values, the better it is. That kind of makes sense. Like you just, if we have huge volatility, just makes it makes everything hard to predict. So, if we have, very small volatility in our values, then the beta 1s, beta 2, like our model will be much easier to estimate and it will have much less volatility. That's for sure. As n goes up, the variance goes down. That's, a property of every sampling property has every sampling sort of distribution has this property. Another thing is the higher the values, the further away the observed values are from the mean, the more precise is your model. I think I talked quickly about this yesterday, but you know, if your observed values are enough, like if this is the mean right here, and all your observed values are really close to the mean, it's really hard to fit a line through the values you have right here. Whereas if they're really spread out, then if they're really spread out across like something like this, it's really much easier to estimate a line through the data points. You probably saw that with the linear regression model as well. And as I pointed out right here, collinearity, that's what happens when your independent variables are correlated. That's the issue that arises. All right, so distribution of the least square estimates, that's what I was talking about before. We know that if the error terms follow a normal distribution with mean 0 and variance sigma squared, that will be the distribution for our independent variable, sorry, our dependent variable yi, which is with mean this and variance sigma squared. But again, as I said, the estimators of the linear function of the dependent variable, the estimators are linear functions of the dependent variable. So we have essentially b1, which is a function of yi. Well, actually, bk is a function of yi for all k. And since it's a linear function of the dependent variable, which is normally distributed, then the bk's also follow a normal distribution with mean beta k and variance of bk. That will depend on a multitude of factors. So again, we can standardize that. If we just subtract the mean and divide by the standard error, then we get a new random variable which follows an N01 distribution, so the standard normal distribution. And usually, as I showed before in the example right here, we can't really get the variance of B2 because we don't really have this population value right here. So we get the estimate for the variance of B2, and that's for all the BKs from B1 and B2 up to BK. We get the estimate right here. And in turn, this new random variable right here will follow a T distribution with n minus k degrees of freedom for all k. Looking forward, if we just extend this to linear combinations of estimators, well, we talked about the B1, B2, B3, B4, their sort of a distribution. But what if I took some, let's say some constant C belonging to R? And what I did here is take a linear combination of all the different parameters that we have, call it lambda, and let's say lambda is equal to C1 beta 1 plus C2 beta 2 up to CK beta K. Well, obviously we don't know the values of beta 1, beta 2 up to beta K. So we'll estimate our lambda with lambda hat, which is estimated by C1 B1 up to CK BK, where B1 up to BK are the estimates for the betas. So this is a linear combination of random variables, B1 up to BK. And all the B1s up to BK, as we've seen before, they follow normal distribution. So the lambda itself will also follow a normal distribution. And similarly, if you standardize it, if you standardize this by taking, by subtracting off the mean right here, this term and this term are exactly equal as far as I'm concerned. And you divide by the standard error of lambda hat right here, which is equal to this. The estimate of the standard error, because, well, because right here, these are estimates, then this will follow a T n minus K distribution as well. So yeah, so that was more or less what we talked about yesterday. Now I'm quickly gonna go over interval estimation and, if I have time, hypothesis testing. All right, so, you know, I'm just gonna do this. Plug my phone somewhere else. Let's see if this works. Yeah. Yeah, oh, good. All right. So now I'm going to hit on what we didn't talk about yesterday, which I wanted to, but I think I rushed through things a bit. So interval estimation, what we want to do is we have our estimates for beta 1 up to beta k, which are the B1s up to the BKs. But we would like a sort of confidence interval where with some level of certainty, let's say 95% confidence, 95% certainty, we know the real value beta k will be in that interval. So to do this, we're gonna use the fact that I shown before that, well, first we had that beta k followed this distribution right here. A normal distribution would mean, the BK, sorry, followed a normal distribution would mean beta k and variance, well, the variance of beta k. We are able to standardize this, and here as well, to a t n minus k, to a distribution following a t n minus k distribution. So the idea here is the random variable bk minus beta k divided by the standard error of bk. Let me put a hat on that because it's an estimate for the standard error. That in turn will follow a t n minus k distribution. And the immediate consequence is that, well, the probability of minus the critical value from the t distribution with 1 minus alpha over 2 level of confidence and n minus k degrees of freedom smaller than this random variable right here, which follows this distribution, smaller than this value right here, is equal to 1 minus alpha. So this is exactly the same procedure as you've seen in 250-71 in terms of how to construct the confidence interval. You just find the critical values of the t distribution at some level of confidence alpha, and your random variable will find itself in between those values with 1 minus alpha level of confidence. The sort of logic behind that is, oh, sorry. You know what? Let me just draw this. Wow, it's not great. There we go. The idea is that, well, if this is a t distribution with n minus k degrees of freedom, if let's say we have alpha is equal to 0.05, well, we have a value tc and a value minus tc. So this value right here is this one, and this value right here is this one. And here we have 0.95, 0.025, and 0.025. And we are the probability that our random variable, which is bk minus beta k divided by the standard error of beta k of bk, sorry, the probability that it's in this bandwidth is 0.95, which is 1 minus alpha, which I wrote down here. And I can just rearrange the terms. My goal is essentially to isolate beta k. And by isolating beta k, which I did right here in this expression, we found that, well, the probability that this term right here, smaller than beta k, which is smaller than this term right here, is equal to 1 minus alpha. And in another way of saying this is we're 1 minus alpha % sure that bk belongs to this interval right here. So that's the general formula for interval estimation for the parameters of our econometric model. I think I have a small example here. Yes, if we consider linear combinations of coefficients. So if we have sales, which is a function of advertising and price, we say sales is equal to beta 1 plus beta 2 advertising plus beta 3 price plus an error term. Let's say, for example, price goes down by 40 units, and advertising goes up by 8 units, well, 0.8 units. actually, so, no, sorry. It goes down by 0.4 units. While the change in sales is going to be equal to well, it's going to be equal to what we have after, which is, well, advertising plus 0.8 units and price minus, sorry, 0.6, not 0.4 units, minus what we originally had before. And so that's essentially our change in sales, which is equal to 0.8 B3 minus 0.4 B2. And if we want a 95% interval estimation for that, then we can just use the property that lambda hat, which is right here, minus lambda divided by the standard error of lambda hat follows a t n minus 3 distribution. And we just apply the same logic right here as discussed above to get an interval estimation. I don't want to go spend too much time, but I'll send the notes and you guys can review more or less how that was done. The last extension of that is hypothesis testing. Let's say we want to know, well, let's say we get an estimate for beta k, which is bk, and we want to test if the true value beta k is equal to some constant c, and versus not equal to some constant c, which is what we have here. Essentially, we're testing if the beta k is not equal to some value right here, which is that constant c. And the way you would do this is, well, you would construct your test statistic as you guys seen in 257 D1. The way you would do this is you take the estimate for beta k, which is bk, minus c, sorry, I have it right here, bk minus c divided by the standard error of bk. And that will be your test statistic. You sort of calculate this and you would compare it to the critical values, the two critical values. And if you're in between those two critical values, which is measured by the critical value from the t distribution with n minus k degrees of freedom and alpha over 2 level of confidence. And here 1 minus alpha over 2. If your critical value if your test statistic is in between the critical values, then you would fail to reject. And if not, you would reject, saying that there's, well, a 1 minus alpha probability that beta k is not equal to c. Here we have a small example. Let's say sales is a function of price and advertising. We want to know if a decrease in the price leads to a negative or zero change in sales, which is essentially asking if give me a second, sorry. Yeah, sorry. I think the logical way we should be looking at this is, should a decrease in price lead to an increase in sales? Like, that's the intuitive reasoning behind it. Like, you would expect that if price goes down, then the sales should go up. And the way you would measure this is by seeing if there's a negative correlation between the price and sales, and that is measured by B2 being negative. So we want to test if beta 2 is smaller than 0. And the way we do this is, well, we would set what we want to see as the alternative hypothesis. So HA would be beta 2 smaller than 0, and H naught would be beta 2 equal to 0. And then we would do this. We would calculate the test statistic by taking B2, our estimate for beta 2, minus 0, which is the value of beta 2 under the assumption that the null hypothesis is true. And you would divide this by the standard error of B2. Oh, we got somebody else. Yeah. All right. So that's how you would go about it. You get the test statistic like this, and you would compare it with the critical value TC, and the critical values by obtaining it's by looking at the table of the t distribution with n minus k degrees of freedom and the 1 minus alpha level of confidence. And if your test statistic right here is bigger than the critical value, then you can be sure that you can fail to reject the null hypothesis. And however, if your test statistic right here is smaller, if t right here is smaller than minus tc, actually so no, plus tc, then you would reject the null hypothesis. And rejecting the null hypothesis just means that, well, you have a 1 minus alpha certainty that actually beta 2 is smaller than 0. Again, we can just do the same thing. Well, we can just do the same procedure for different examples. I'll just write one example down. Let's say our model gives us sales, which is equal to beta 1 plus beta 2 advertising plus beta 3 price plus the error term. And we estimated that by sales being, let's say, 0.3. So sales hat, because that's the estimate, plus 0.7 advertising, minus 0.2 price, plus, no, that's about it. And with the error term, 0.05, 0.07, and 0.09. All right, and here, one question we could ask amongst many questions is, does an increase in advertising increase sales in such a way that that the cost of increasing advertising is compensated for. And what I mean by that is, if I increased advertising by 1 unit, which would cost me one unit, let's say, to make things simple, would the sales increase by more than 1 unit in such a way that it would then cover the cost of advertising? So we want to see if beta 2 is greater than 1. And since we want to measure this, we'll put this as our alternative hypothesis, and our initial or null hypothesis will be just beta 2 equal to 1. So that's what we want to check. H naught beta 2 is equal to 1. HA beta 2 smaller or equal than 1. Greater than 1, my bad. To make sure it covers the cost. The increase of sale covers the cost of increasing advertising. And the way you do this is, well, we would construct our t-test, which is equal to beta 2 minus beta b2 minus beta 2, under the assumption that the null hypothesis is actually true. So if the null hypothesis is true, then this is equal to 1 divided by the standard error of B2. All right. And the way you would measure this is, well, you have your estimate for B2, which is equal to, well, that's equal to 0.7 right here. Subtract it with 1 under the hypothesis, under the assumption that the null hypothesis is true, and divide by the standard error of B2. And so you have this value, which I'll call, let's say, gamma. And, well, as we can see right here, this is a right tail test. So if gamma is greater than the critical value with n minus 3 degrees of freedom, and alpha level of confidence. Well, if that's the case, well, then you would reject null hypothesis. And on the other hand, well, otherwise, fail to reject. And if you reject the null hypothesis, on the other hand, well, you're 1 minus alpha percent sure that beta 2 is indeed greater than 1. So in other words, if you reject the null hypothesis, you're 1 minus alpha percent sure that indeed, if you increase advertising by 1 unit, the increase in sales will cover the cost of increasing advertising by 1 unit. So yeah, that's about it for today. Not much. Is there, let me look at the chat. Is there any question you have, Liang, or regarding anything? Or
I guess it's fine for now.
Okay, I guess it's a bit confusing because you guys didn't tackle the subject yet, and I don't know. I just wanted you guys to explore a bit what was going on. But I'll post my notes and then I'll upload this this recording. I don't think I'll be able to upload the first one because I don't know if you were there. I got disconnected, so I think I might have lost the recording. But I'll definitely upload this one, which is the reason why I came back over the stuff we did at the beginning. And yeah, that's about it. All right. So if you don't have any more questions, I wish you a very good day.
Yeah, thank you so much. It's really
Take care.
appreciated.
No problem. Take care.